What I would like to focus on today is a specific direction which has to do with the passive and active facets of quantum steering. The work has been done in collaboration with Yaroslav Gerasimenko and Igor Gorny. So, measurement. Measurement comprises three steps. The first step has to do with coupling the system to a detector via some system detector Hamiltonian. If the coupling is weak, we are talking about weak measurement. If the coupling is strong, this is strong measurement. And depending on weak or strong, the system and detector are weakly or strongly entangled. Then after time delta t, we decouple the system from the detector, and then we read out the detector, meaning that we project the detector in the desired direction. Now this readout of the detector will have a back action on the system, which usually is bad news, but the question here is whether we can harness the back action for something good. Or in other words, whether we can repeat the measurements, accumulate the back actions, and then guide or steer our state towards a desired target state, whether we can engineer a quantum state. So our wish list is quite ambitious here. We want to have a specific state to steer towards. Then we want to start with an arbitrary initial state, which in general is unknown to us. We want the protocol to be robust against any perturbation that may occur in the middle of the protocol. We don't want to have a fine-tuned time for the operation. And lastly, the target state needs not be a ground state of a known Hamiltonian. So these are the principles of quantum steering. First, we prepare the detector qubits in a given initial state, which is independent of the running state of the system. At each step, the detectors are prepared in the same state. Then we couple the system to the detector. We let them evolve to a unitary evolution operator. And as a result, the system detector density matrix at time t plus delta t is given by their state at an earlier time t, which would be the product state of the detector times the running state of the system, evolved in a unitary manner. So the question is what we do once we have it. And here there are several options. One option is to say, I'm not interested at all in what the detector has shown me. I throw away the detector and I start again with a new detector, which will amount to a tracing out over the result of the detector. And this I will call blind steering, which is a specific instance of passive steering. The steps of the steerings are predetermined. They do not depend on the running state of the system. But there are other paradigms. Another paradigm will be a post-selective steering, where I consider one particular sequence of readouts. And if the actual readout is not that, I throw away the experiment, I start again until I obtain the desired readout sequence. I will not talk about it today, although it's quite interesting. And the third one, which I'll discuss later, has to do with active decision-making steering, active feedback steering. So let me give first a couple of examples concerning passive steering or blind steering. First, a trivial example. The system is spin 1/2, pointing in any direction on the Bloch sphere. I want to steer it towards the North Pole. So I have the system state and the detector state. So the system state is arbitrary. At each step, before I start any measurement step, I tune the detector towards state up. And I let the system detector composite evolve with this unitary operator, which depends, of course, on the system detector Hamiltonian. And for our purposes, steering the system towards the North Pole, this is the system detector Hamiltonian, which conveniently can be written in this way. Now, already here, we can learn something very important. Note that if the detector is prepared in the state up, then this part of the system detector Hamiltonian acting on this state will annihilate this state. So the only state that takes place in this dynamics is this one, and this is what gives our steering directionality. To obtain the system state after the step n+1, we take the state of the composite system and detector at step n, which will be a product of the running state of the system times a projection onto detector state up. We evolve it with our unitary evolution and trace over the detector. So these are a couple of examples to see how this works in reality. I parameterize the state of the system with in this form. S is a vector of the coefficients of sigma x, sigma y, and sigma z. Here I start with a pure state. Here I start with a mixed state. But we see that in any of these cases, after an order of 120 steps, we are basically there. The system is oriented in the direction of the North Pole. Example number 2. Let's take a many-body system, which is weakly entangled, the AKLT chain, which is a chain of spin 1. Its Hamiltonian is written here. We take each link, each pair of neighboring spins, and we project the total spin onto the sector of total spin equals 2. Now, clearly, the ground state would be when all these terms are 0, meaning that each bond, each pair of neighboring spins has 0 weight in the total spin equals 2 sector, has only components in the total spin equals 1 and total spin equals 0. Now, here are several, 3 requirements, basic requirements we want from our steering in order to be reasonable, to be implementable. First, we want the measurements to be local. Second, we want the number of detectors not to scale up faster than extensive, not to scale up faster than proportional to the number of degrees of freedom of the system. And secondly, we wanted the complexity of the system detector Hamiltonian of each detector will not increase when the size of the system increases. And this is exactly what we have here for the AKLT. We have a system detector Hamiltonian, which assumes the general form of sigma minus detector times something, sigma plus detector times something, and this something consists of 5 operators. For this blind steering protocol, if we take the continuum time limit, we obtain a Hilbert equation, and the U's play the role of jump operators in the Hilbert equation. Yes?
I have a question. Just to have an idea, is this coupling between the environment and the system local? So is any detector only coupled to a few spins?
Yeah. So here you see. In this case, each detector is coupled to 2 spins.
Okay, yeah. Fine. Thank you.
Yeah. Otherwise, it will not make sense to okay. So if we have a single link, a single pair of spins, then steering out of the total spin equals 2 sector is not unique. We can do it in many ways. But if we have competing steering operators which do not commute, steering operators of neighboring links do not commute, then there is only one way to do that, and this is indicated here. This is the reduced density matrix of a link as it evolves this time, and we see that asymptotically, each reduced density matrix of a link is diagonal, has 0 components in the sector total spin equals 2, and has diagonal components here, and the values of these diagonal components is given by here. And indeed, if we check the a convergence of our initial state towards the target state, using either the Frobenius norm or the trace norm, we can see that this convergence is exponential in time. So this is what I wanted to say about a passive or a blind steering, and now I'm moving to active steering. So before that, before I start, let me mention very briefly the differences between passive and active. So for the passive or blind steering, the steps are the following. We have, in a given measurement step, we start with a product of the running system state times the reset state of the detector. We evolve them in a unitary manner. We have a detector with possible readouts 0 or 1, but we trace out the detector. This tracing out of the detector will have back action on the system. And then the next step, we start with the modified state of the system and the reset state of the detector. This is for our blind steering. Now, when we come to active steering, there are two new ingredients which are essential. First, we keep track of the readouts. So this is our vector of readouts, 1, 0, 0, 1, 0, etc. Second, we want to be able to cleverly use this history vector in order to decide what would be our next unitary evolution operator in the next measurement. And we want to do it such that the runtime becomes shorter, the fidelity becomes bigger. So there are two elements here. First, at each step, we need to have multiple system detector Hamiltonians to choose from, and they should not be related to each other in a trivial way, so they should not commute. And the second element, we need to have a policy how to use our readout history in order to choose which system detector Hamiltonian to use now. And what I'll do the rest of my talk is I will give you the flavor of two such decision policies. The first one is a quantum compass or a cost function policy. So we introduced a global cost function, which is a function of the state of the system. And we arrange it such that when we reach the target state, it is a minimum. For example, the infidelity R of the system state rho S with respect to the target state psi S, which is defined this way. So it is always positive. When we reach the target state, it is 0. And now the objective of our objective is to find a sequence of steering operators of system detector Hamiltonians that brings the system to the global minimum of this cost function in the fastest expected time. Now, this is too ambitious because we need to have a global overview of both spatial and temporal evolution of the system. It's too costly. So we are replacing this by a cheaper, greedy version of this. Namely, we would like to find in each step the system detector Hamiltonian, the steering Hamiltonian, such that it will give us the fastest expected reduction of the cost function in a single measurement step. So let's see how it works with the AKLT case. In the AKLT case, we have the sector of total spin equals 0 and total spin equals 1 of a link, which is spanned by 4. I ran out of by 4. Let me try to see if this works. Yeah, by 4 vectors, and then we have 5 vectors with components in the excited sector of total spin equals 2. we define those V operators which appear in this combination with the sigma plus and sigma minus of the detector. And we then define a navigation strategy. So we iterate cyclically over all bonds, all neighboring spins, and we optimize the matrix C to give us the fastest reduction in our cost function. And this is to be compared with the passive measurement. And this is our result. So this is a histogram of the time it takes us to reach a fidelity of 99%, infidelity of 0.01. Look at the histogram, which is cut here. It should continue here. For the passive protocol, the histogram for the active protocol. And you can see that the gain we have with the active protocol, the relative gain, increases as we increase the size of the system from 3 to 4 to 5 to 6 spins. And the ratio of improvement reaches at a length of 6 to an order of magnitude, and presumably will be higher for a longer length. Now, yeah.
Can you assess how much more time it takes to apply the modification to the measurement? That's also kind of an operation that needs to be done.
Yeah. So.
Your time is applications of the measurement, right?
Mm-hmm, yeah.
Is there a hidden cost?
Yeah. So absolutely, the hidden cost is that we need to use a classical computer to do all these operations, all these optimization. And for what you have seen, it's, I would say, a couple of tens of hours in a computer. But if you ask me what is the rule, I mean, how this time increases with the system size, I don't know. It's a good question. I don't have any assessment on that. So there is well, it's a very good, you got me into this point I was trying to, yeah. Yeah.
Because there are, as you said, 4 states, and with active control, you are steering towards the closest one.
Say it again?
So the gain in the speed with active control, is it because, as you said, there are 4 states, and you can dynamically figure out what is the closest one, and you are steering?
No, it has nothing to do. What we are using here is we are using periodic boundary conditions, so we have only one state. So forget about degeneracy. I mean, we can do it also for the degenerate ground state, but we wanted to move it. Only one ground state. Okay, there is a big caveat here, which needs to be taken very seriously, and I would like to demonstrate it with an absolutely stupid and trivial example. So imagine that my target state is 0, 0, 0, 0, product state. And imagine that my initial state is 1, 1, 1, again, a product state. So now suppose I have a sequence, steering, that gradually brings me to the 0, 0. From 1, 1, 1, 1, I go to 1, 0, 0, 1, 1, to 1, 0, 0, 1, 0, etc. What happens is that for all these intermediate states, those intermediate states are orthogonal to the final state. So if I apply this global cost function, I will not be able to see any improvement, or the landscape for the global cost function is completely flat. And this has the flavor of Anderson orthogonality catastrophe. So in order to overcome this, one can invoke the concept of local cost function. So with the local cost function, I take the reduced density matrix. I trace out everything except segment alpha. Similarly, I do it for the target state, and I calculate the cost function of those reduced density matrices. And with those reduced density matrices, I will see improvements of the landscape will not be flat, and I will see that I actually improve as I approach the target state. Okay. I guess I have 5 minutes. Okay, so now I go to the second and last policy I would like to mention here, and that has to do with the quantum state machine. So imagine that I span my Hilbert space by a certain set of vectors. Each vector is represented as a vertex. And now, with the steering transformation, I can have a linear mapping between a given vertex and a superposition of other vertices. So I have a graph. Now, given this steering operator, I will have a graph when my detector clicks, and another graph when my detector does not click. So I have a mapping lambda click and lambda no click. And if I have several system detector Hamiltonians, I will have different graphs. So the quantum state machine consists of combining all graphs to a single colored graph. So that will be a trivial example. I have 3 vertices. I want to go from the initial 0 to the 2. I have 2 system detector Hamiltonians. 1, and I have a graph for H sigma system detector Hamiltonian when it clicks and when it does not click, and system detector Hamiltonian number 2 when it clicks, when it does not click. And here it's a trivial one. I have a semi-classical case. It's clear what I need to do in order to go from 0 to 2. So, but this classicality is basis dependent and is a very special case. So in general, I will have a box, let's say, with 5 vertices with colors. So the black graph will correspond to a superposition. The red one will correspond to interference, and the silver one will be semi-classical. But if I rotate the basis, I take a symmetric to anti-symmetric combination of these 2 vertices. What used to be the black is now semi-classical, and what used to be the semi-classical silver now becomes interference. So all in all, for this block, I cannot find a combination which will reduce all the vertices, all the connectivity to a semi-classical conductivity. So this is an irreducible quantum block. And the idea behind this quantum state machine is to divide my Hilbert space into boxes, irreducible boxes, which are connected semi-classically. So there is lots of subtlety here, which I'm skipping because I don't have the time. Let me show you an example. So the example is a 3-qubit state, which is called the W state, shown here. And my initial state is a stupid product state 0, 0, 0. So now I have my system detector Hamiltonian with the V operators coupled to sigma detector plus and sigma detector minus, and I use 4 V operators. Here is a comparison between a passive protocol and active protocol. This is the same histogram of the time it takes me to reach a fidelity of 0.99, and you can see that I gain a factor of 20. So, sorry. So I'm essentially done, and I want to throw at you some of the challenges, not all, but a partial list of the challenges for the future. First, I would like to understand better how to be more efficient and scale up a system size for, say, AKLT chain. Second, the rules of playing with the local cost function as opposed to global cost function are still to be better understood. The role of frustration is, at the moment, not really understood. And finally, a more ambitious task would be not to engineer a state, but to take a state and rotate it, manipulate it, perform logical gates, or perform error corrections with this active decision making. And with this, I would like to say thank you.